So, we're going to start today with the notes, and all of these units that I'm giving you guys, like 1-1, 1-2, 1-3, is how AP has broken up this course, and they've named them all. So first of all, I'm using Brian Passwater stuff anyway, but I'm going with the names that they use. And this first one I found really interesting because it is called Change in Tandem, and I have not really ever heard the word tandem used in math classes a lot, and I've taught for a while now, and I've taught most math classes. So I thought it was very interesting that this was the very first unit that they called Change in Tandem. You know, having not seen it before, I was trying to think, like, where have I heard the word tandem before? Two things I think of whenever I think of tandem is a tandem dump truck or a tandem bicycle. Bicycle is probably the better picture to look at here. Tandem bicycle is the bicycle that's got the two seats. So you ride the bicycle together, and it's so romantic as you ride on through a beautiful park. My husband and I would definitely be in a fight pretty quick if we tried to ride this tandem bicycle, I'm pretty sure. But when you're on the tandem bicycle, you have like one goes with the other, right? So if the first person goes, the second person's going to go too. Even if the second person is not pedaling, it just makes it harder on the first person, but you're going to go. So that kind of is a good picture of what we're talking about here. When we're talking about change in tandem, we're talking about, typically we're going to be looking at two variables, and we're talking about how if this variable change, what happens to this variable over here, right? Because those two are related to each other. So that's what we're talking about. The first part here is going to say a blank is a mathematical relation that maps a set of input values to a set of output values such that each input value is mapped to exactly, this is going to be one output value. Anybody know what goes in that first blank? Function. Good job. Now, I left this here. I thought about taking it out, but I didn't. Below this, you see, in previous courses, you may have used the vertical line test to see if a graph is a function or not. That was where we took that vertical line and we went across, and if the function hit twice anywhere, it was not a function. Later in this course, we will learn that this test does not always work. I Googled this, and I could not figure out when the vertical line test does not work. I am unaware of this particular scenario. So I left this in here, and maybe all together we maybe later in Mr. Passwater's notes are going to figure out when vertical line test does not work. But I'm putting a question mark there and warning you, I don't know when that is. So he must be smarter than me. So hopefully we'll figure that out. But if we don't, I don't think it's going to really impact our lives very much if we just live our lives thinking the vertical line test always works. So that's there. Input values are called the domain. And that is represented by the independent variable. Now, I've got all this definition here, and it talks about input values, domains, independent values, and I've not used the letter we think of most. What letter do you think of whenever you think of a domain? X, right? It is typically going to be your X variable. I'm going to put it there in parentheses. It does not have to be the X variable. Sometimes the independent variable is time, and they use a T. So it doesn't have to be the X variable. But if you are using X's and Y's, it is going to be on your X-axis. And if you had Coach Wood, then you know all of his X's live in Texas. And Dallas is a city in Texas, and Dallas starts with a D like domain, so X is domain. How many of you had Coach Wood for Math 3? Okay, most of you. How many of you had Miss Martin? Okay, and did anybody have Mr. Brown? I've only got one person that Mr. Brown. So I will say there's a big difference between Coach Wood and Miss Martin, for sure. Coach Wood is a special teacher that I'm glad that those of you had him, got the chance to have him before he was gone, because he's not going to be, nobody else is going to be able to say they had Coach Wood after now. So, but definitely they do things differently sometimes, but I have usually found that there is not like most everybody's able to catch on in here. There's a lot of overlap between Math 3 and pre-calculus, so some of the stuff maybe was confusing to you in Math 3. We kind of go over again in here and go a little further with it sometimes. So usually I don't run into a lot of big issues where everybody that had one teacher is doing really well and everybody that didn't is not. So I think we'll be okay on that. But if there is something that maybe I'm assuming that you already know and that is a false assumption that I have made, just let me know and we can go back over whatever it is that you are having trouble with. It might be you've just forgot it, or it might be the whole class never learned it. So we will we can look at that anytime. All right, the output values is your range, and that is usually represented by the dependent variable, which does not have to be the y, but is a lot of times the y. Okay, so function rules is something we're going to focus on a lot here. And so these two examples are here for us to practice a little with function rules. And they're given in the two ways that are a little less common for us to see. One of the big focuses that AP has about math in general, it's just a really good practice for math, is looking at multiple representations. And there are 4 of them that they want us to focus on. The first is to look at things numerically, which is like in a table. So we see a table here. The second is to look at them in a graph. So if you graph what's on the table, you'll see the graph. The third is to look at function rules, like algebraically. So that would be something like y equals 2x plus 4. And then the fourth is one that I feel like we probably leave out a lot in math classes because us as mathematicians don't like it. And that is to look at things verbally, to look at like written explanations of them. And that's what you're seeing in part A. As a mathematician, I try to use as few words, written words, as possible. We even, as mathematicians, come up with symbols for words so we don't have to write the words anymore. Like in math, this symbol right here means therefore. So if you don't want to write therefore, you could just put those 3 dots and it means therefore. So we kind of shy away from this, I think, sometimes, but AP is really going to force us to look at it a little bit more because there is going to be free response parts on your exam where you have to write out an explanation. So we'll work on that more. So we got the function f halves each input value and then adds 1. So there's some different ways that we can think about this. Like we could start just by doing this to numbers. So like if I plug in 0, right? I'm supposed to half the input value, so half of 0 is 1, half of 0 is 0, and then I add 1, and I'll get 1, right? So I could graph it. Let's do both at the same time, 0, 1, there it is. And then I could try 1, and if I plug in 1, I'm going to take half of 1, which is 1/2, and I add 1, which is 1.5 or 1.5. So I got 1, 1.5. I could graph that. I could do this again. 2. Half of 2 is 1. 1 plus 1 is going to be 2. There, so I got the point 2, 2. Now, I could continue with this and just use the table to help me graph this here. But another thing I could do is I could write a function rule for this. I could do f of x equals here. So if my rule is that I'm taking half of the input value and then I'm adding 1, who could tell me what that would look like in an equation? Okay, so you could use like x divided by 2 plus 1. That worked beautifully. I was actually going to do it differently, so I'm glad you said it that way. That works wonderfully. Was anybody else thinking anything different? Because I was thinking something different that would be equivalent, but yeah, I was thinking 1/2 times x plus 1. Is there any difference between multiplying by 1/2 and dividing by 2? They'd be the same, right? These are equivalent to each other. That second one should make it kind of clear to you what type of graph are you going to get from this. Is it going to be linear, right? So what is the y-intercept of that line? 1. What is the slope? 1/2, which means you go up 1 over 2. So if I want to finish graphing this without doing the table, I could just go up 1 over 2, up 1 over 2. I could go down 1, left 2, down 1, left 2. I could get these points, draw in my line right here. So this gives us a lot of different ways of looking at the same function, right? We have words, we have a graph, we have a table, we have a function rule. Those are all, and they're all related. They're all the same function represented in different ways. And we want to look at that a lot because that really helps us understand so much more about math. All right, B, all we have is a table for B. So for B, if we graph this, we would just have to graph the points. So we've got -4, -1, we've got -1, 2, we've got 0, 3, 2, 3, and 4, 1. Now, that's all we know about that function. That's all we can do. We can't write a rule for that. We can't draw a line connecting these. There might be more points that are not given to us in this table, but we don't know that for sure. So that would be all that we could know for sure about this graph. Okay, so this chart down here at the bottom is going to be really important, and we're going to talk more about it even tomorrow as well. But we're going to be talking about behavior of functions here. I'm pretty sure you should have already talked about increasing and decreasing. I know I did that even with my regular Math 3s last semester. So you should have talked about increasing and decreasing and what that means for a graph. Have you guys heard the terms concave up and concave down before? That is unfamiliar. Okay, so that is something that is going to be new but is really not all that difficult to figure out. So I think you guys will be good with it. So whenever we're talking about a function increasing and decreasing, as the input values increase, the output values always increase. So as our x increases, our y increases, right? As we go over to the right, we go up, right? So whenever you're thinking about something increasing and decreasing, you're always looking at the graph left to right here. So, like, for example, this graph is always increasing. If you start on the left side, it goes up the whole time. Now, let's talk about the mathematical definition of that, and that's this part right here. Because this is something I'm going to try to look at a little bit more here. The mathematical definition of something increasing is that if A is less than B, then f of A is less than f of B. Okay, let's talk about what that means, why this matters. What it's telling us, A and B are going to be values on our x-axis here. F of A and F of B are going to be values on the y-axis because whenever you plug a number into a function, you get the output value out, the y value out. So A and B could be any two numbers. I could pick any two numbers. Let's pick 1 and 3 right here, right? It is true that 1 is less than 3. So what that means, if this is increasing, f of 1 should be less than f of 3. So 1 is right here. It's clearly less than 3. That's easy to see. And to find f of 1, I would go right here. It would be this point right here, and it'd be the y coordinate that goes with it. So f of 1 would be here about 1. And then f of 3, right here, there's my point on my graph at 3. So the y coordinate that goes with it is somewhere around here, 2.5-ish. That's f of 3. So since 1 is less than 3, we would know that f of 1 would have to be lower than f of 3. Now, for something to be increasing, this has to be true for any two numbers on the whole graph, right? So 1 and 3 definitely worked, but 1 and 2 would have to work, and 1 and 1.1 would have to work, and 0 and 7 would have to work. And obviously you can't like test every one of this, but overall it's just, you're just thinking about it going up there. But I think it's, when we get to some finer points of things, it's helpful to see at least that formal definition presented there. Decreasing is a similar definition, but instead of f of a being less than f of b, f of a is greater than f of b, right here. Concavity we're going to talk about more and more as we go along here. The very most simple thing I can tell you about concavity is that something that's concave up is sort of curved upwards, right? It looks sort of like a U shape. Concave down is something that's curved downwards, right? We're going to talk about the rate of change being increasing and decreasing more here in a little bit, but I'm not going to go into great detail on that right now. There. So let's look at this example right here. This particular example tells us the graph of h of x is shown above. Use the graph of h to find open intervals where h has the following behaviors. All right, so one thing I want to see what we know about is this says open intervals right here. So you should be hopefully familiar with using both interval notation and inequality notation. So, for example, the domain of this whole graph, just to give you an example of interval notation, the domain of this whole graph goes from -4 to 7. Now, oops. Now, if I want to use interval notation, I've got to put either parentheses or brackets on the end of that. Okay? So, does anybody know what I would use? Would I use a parentheses or a bracket? Bracket. Why do I use a bracket, Joshua? Well, no, that's not the reason. Although it is very interesting, like some countries, when they use interval notation, don't use parentheses for that very reason, because it's confusing. It looks like when you got parentheses -4, 7, that it is the 0.47 or -47. So for that very reason, some countries do not use the notation I'm about to show you, but the good old US of A does it this way. So, and actually AP on the final exam will accept, like, if there are standard things that other countries do, they will accept it as an answer. So I'll show you the other thing that some people do. But like, let's make sure everybody knows. Does everybody know this? This is I did not know this till like 3 or 4 years ago, which is crazy because I'm a math teacher and I should have known this. But we write 1,200.75, right? That is 1,275 hundredths, right? Do you guys know that lots of other countries do it this way? That the comma is the decimal point. I did not know this until I was like 4 or 5 years ago. Paloma, that's the exchange student this year, Argentina does it this way. Several times she'd show me her calculator and she'd say, it's not working, I don't know what I've done wrong. And she had something like this in 1 point. She put a comma instead of a decimal. And I thought that was crazy that I did not know that before. But that has nothing to do with what we're doing right now. But just thought I'd throw that in there. Bonus for you there. The reason that we use brackets on this one is because you have closed dots right here. And that means we're including those endpoints, right? If we were to write this with inequality notation, it would be -4 less than or equal to x less than or equal to 7. We would put the or equal to's with those less than signs because we're including those points on the end. So if I were wanting to know this domain, then I would use this. So let's put ourselves a note over there. I'm going to erase this because it was just a fun fact there. If you have brackets, the endpoints are included. Okay. It's like having a less than or equal to sign instead of just a less than sign. If you use parentheses, the endpoints are not included. So if this graph had like open circles on the end showing us that those points were not included, then we would use parentheses instead. So I said all that to tell you guys that open intervals means the endpoints are not included. So we want to use our parentheses for this. Okay. Now, what AP is doing here by saying open intervals is they're avoiding a controversy. Because the controversy is this right here. Let's talk about this point right here. No, not that point. Yeah, that point. That's fine. Let's talk about that point right there. If you're talking about that particular point, right, is the graph increasing or decreasing at that point? Well, depends on what side you look at, because if you're coming over here, there we go, and decreasing, right? Boom, decrease down to that point. If you start right here and you look at this side, what's it doing? It's increasing. Uh-oh. Poor Finn. So, my calculus teacher in high school taught me that that point was neither increasing nor decreasing, and you should not include it. However, if we look at our graph, if we look at our definition of increasing and decreasing that we talked about, it said that if 3 is less than -2, right, 3 is less than -2, that is true, then we got this is greater than that, so you'd still be decreasing at that point. So it would be included. So most definitions are going to go these days that you should include those points. But what they have done here is they have told you open intervals because some textbooks are written different ways. They are avoiding controversy on that. So that is what AP does when there are controversies, mathematical controversies. They just avoid asking about it. They have specifically told you open intervals, so we're going to use parentheses on everything. So that's what we're going to do here. Let's do some more. We want to know, first of all, where H is increasing. So we're just thinking left to right where this graph is going up, right? So that's this piece right here and this piece right here. Okay. Now, whenever you are reporting this, you are telling me the domain where this is happening, the X values where this is happening, right? So what I like to do is I like to think of taking like a vertical line and sectioning this off right here. So this section right here, I'm taking those vertical lines and I'm chopping off that piece of the graph where my graph is increasing. And I'm going to look at where those vertical lines hit that x-axis, and that is my domain. So this would be -2 to 0. There. That also can be written this way, -2 less than x less than 0. We're probably going to use interval notation a lot more. That's the parentheses and the brackets. But that second notation is also valid, so we need to be familiar with both of those. All right, so that's the first place where we're increasing. We're also increasing right here on this section right here, which is from 4 to 7. So I'm going to use this U right here. That means union. So it means that we're combining these two to make our answer, and that is going to be 4 to 7. Or if you want to write it this way, you could do 4 less than x less than 7. We're not even going to get done with this. Gosh, I talked too much. All right. So, decreasing. We're looking from here to here. We're decreasing. We're also decreasing over here. So, again, we're looking at x values where this happens. So, that would be -4 up to -2. And then this next section right here would be 0 to 4. Now, a big part of me wants to say 3 to 4. What am I doing wrong if I say 3 to 4 right there? I'm looking at that y-axis because, like, when I see that point, there's a 3 right next to it, and it makes me want to say 3. But we got to go down and look at the x-axis only for this. You're not going to report anything from the y-axis when you're talking about these. So it's 0 to 4 right there. Think about taking that vertical line, like cutting your graph. Okay, next part asks for concave up. So we're looking for that curved up shape. Who can tell me where that happens? What do you think, Josh? 2 to 7. So 2 over here to 7, we got that curved up, right? So that would be right here at 2 all the way to 7. Okay, it doesn't ask for concave down, but -2 to 2 is concave down. What about -4 to -2? It's decreasing. What about its concavity? Is it curved? It is not. So that does not have any concavity. If they were to ask about it, it's neither concave up nor concave down. It's just constant. It's constant rate of change there. All right. All right, we're looking for where h is both increasing and concave down for this. Who thinks they've got that? Can tell me where this is increasing and concave down. What do you think, Xander? -2 to 2. It's concave down, but it's not both the increasing and concave down. What do you think, Lucas? -2 to 0. So this part, you're increasing and concave down. But over here, you would be decreasing and concave down. So that would be -2 to 2 right there. I'm sorry, -2 to 0. And then we got decreasing and concave up. So who thinks they've got that one? Decreasing and concave up. Lucas? 2 to 4. 2 to 4. Your graph is decreasing, but it's curved up. Okay, questions on those? All right. We got to do this. Okay. All right, I think 3 is kind of hard to do. It's asking you to graph this, and it's got to have all these, like, characteristics. But all of your intervals are going to overlap, which messes with my mind. So this is what I like to do for this. So I like to make myself a number line, and I like to put all of these numbers on it in order. So the lowest number I see is -4. That's the only negative number I see. Then 1 is next. 3 is next. 4, 5, 6, and 7. I'm about to run out of room right there. All right, and I like to make myself a little chart where I talk about increasing, decreasing, and concavity. So I like to do this because it just helps me keep things straight so much better if I do this. So if we read through it, says the graph of K is increasing from -4 to 1. So from -4 to 1, we're increasing. And 5 to 7. So 5 to 7 right here, we're increasing here and here. And then we are decreasing from 1 to 5. So decreasing here and decreasing here. And then we're going to do the same thing with concavity. It tells us that from 3 to 6, we're concave down. So 3 to 6, concave down. I'm just going to put a down arrow here. And negative 4 to 3 will be concave. Oh, wait. I've got that backwards, sorry. I'm hurrying, I'm messing up. Alright, concave up on 3 to 6. Those should be up arrows. And then negative 4 to 3 is concave down, and 6 to 7 is also concave down. So I have to draw something that has these characteristics. Another thing I like to do is I like to go put me some vertical lines at all of these points. I can make them dotted, but then I'm not very good at making them straight. Ooh, that one's a little off. That's supposed to be at 1. Try that again, actually. 1, 3, 5, 6, and 7. Now, these lines are not part of my graph. I'm just drawing them to help break up my graph so I know what to do. I'm going to switch to a different color here. So, from negative 4 to 1, this first section, my graph needs to be increasing, but concave down. So I need to be going up, but it kind of needs to be curved down, something like this. Now, it doesn't really matter where you start, how high you go up, it just has to have that shape to it. Okay, then from 1 to 3, I'm still concave down, but I switch to decreasing, which means the graph needs to go back down, like that. Over here, from 3 to 5, I'm supposed to be decreasing, but concave up. So I need to be going down, but curved up. So it's going to look like this. From 5 to 6, I'm supposed to switch to increasing, but still be concave up. So increasing, concave up would look like that. And then my last part's increasing, but concave down. So that would switch to be like this. Now, this graph could be taller, it could be shorter, it could cross the x-axis at different places, but it needs to have that general shape to it. Okay, questions? All right, real quick, we need to fill in this table down here and answer 4. And I think that'll get us in pretty good shape to do the assignment I've got for you. All right, so rates of change. If I have something that's increasing, it looks like this. The rate of change, what's another word for rate of change you may have learned? Slope. Good. Okay, if I have an increasing line, what do I know about my slope? Positive. And if I have a decreasing line, then my slope would be negative. Okay, now let's talk about something concave up real quick. Really quick. We're running out of time. Hello? Hello? Okay. All right, so if I look at like the slope for this first little part, is that positive or negative? Let's make an estimate. Let's say it's negative 2. It's an estimate, okay? All right, let's do this next little piece. Positive or negative? Negative, but would it be, what would you estimate that to be, maybe, in relation? Huh? I'd go negative 1. It's going to be less, because less steep, right? The absolute value of that's going to be less. Then, let's just do one like this. What would you say the slope of that is? Flat line, what's the slope called? Or what, 0, right? All right. What about if I have this right here? Now we've switched to a positive. Maybe that's a positive 1. Let's do this last one. Maybe that's a positive 2. As we go from left to right, what's happening to that slope? It is increasing. So if something is concave up, its rate of change or its slope is increasing. And I'm not going to draw the picture for concave down because we're running out of time, but that would be decreasing. Okay, so real fast, let's look at 4. And then this will be enough for you to do your homework if you did not get to the calculator part. All right, so this question says a table is given below that describes the rate of change of a function for which interval is the function increasing in concave down. So this has asked us the function is increasing concave down. So function is increasing concave down. But the chart doesn't talk about the function. What does it talk about? The slope or the rate of change, right? So my slope or my rate of change, if I'm increasing and concave down, that rate of change should be positive and decreasing, right? So positive and decreasing happens right here. So that means the answer to this question would be 1 to 2. All right. So sorry that I went over. You do have an assignment tonight. Let me give you guys this. All right. This is called 2 Truths and a Lie. You've probably played that game at some point. Each picture has 3 statements. 2 of them are true. 1 of them is a lie. So you are going to go through and figure out which one's true, which one's false for these. The key is online, so you can check it to see how you're doing. There, it looks like a lot, but it's really not much because it's mostly just pictures. So hopefully this is not going to take you more than 15 or 20 minutes. All right, and I'll check this tomorrow. And hopefully tomorrow I'll do better on my timing here. I don't mean to keep you over.